So I want to talk a little bit about cell notation because we often draw electrochemical cells. I'm going to go back and for each one of the three reactions we just did, we'll draw what the electrochemical cell looks like, which one's the anode and which one's the cathode. And then I'm going to show you something called cell notation, which is an abbreviated form so we don't have to draw the cell every time. Just a couple of rules generally, though these are not 100% rules. But we usually identify the anode as being on the left side and the cathode being on the right side. And also, the anode is usually considered to be the negative electrode. The cathode is the positive electrode. You'll notice how when we wrote this electrochemical cell out with its voltage, we got a positive voltage with the cathode being on the reduction side, the most positive of the voltages. So we usually assign it the positive voltage, and then the anode, or anode. I had to write the first time. The anode we usually assign as 0 volts relative to the cathode. So I'll talk about that as we do this. Okay. So let's go back through real quick. So the cell notation is anode on the left. We essentially draw a path between the anode and the cathode. And then if we hit a phase boundary, we put a straight line. And if two things are in the same phase, we put a comma. And then if there's any special conditions, we'll note those. And then 2 slashes is actually for 2 phase boundaries and a salt bridge. So keep in mind, those are some of the things we'll be going over as we look at these different electrochemical cells. Okay, so I'm going to draw this one. And so which side is my anode and which side is my cathode? So my anode is my lead to lead 2 plus. So when I'm drawing this electrochemical cell, and I'm going to draw its half cell, I'm going to have a salt bridge down here. I'll have solution in here. Or maybe I'll make it wavy so it looks like solution. And you'll notice that the lead is part of the redox reaction, and lead is a metal. And because it's a metal and it's being oxidized, we're going to just use a lead electrode in solution. So this would be Pb. In solution, we'd use Pb2+, plus, and its concentration would be 1 molar. This would be for a standard electrochemical cell. And now we have a wire going up this way. And this represents, again, the lead half cell. This is the anode half cell. Remember, anode is oxidation, so the lead electrode is actually dissolving to make lead 2 plus, and when it does that, the electrons have to leave in this fashion, like that. Now we're going to draw the other side, the other half cell, and that will be the silver reduction half reaction. And so we'll connect it on the other side of the salt bridge. And then we'll draw, again, our solution. And again, silver is a metal, and it's part of the half reaction, right? So, and I know it may be sounding silly that I'm saying silver is a metal, but you'll see in a little bit, it's not always that the stuff that we're doing the redox reactions on, it's not always that they're metals. Sometimes they're all aqueous, and so we have to introduce a metal to be the electrode, okay? So here's my cathode half cell. And we usually draw a voltmeter in here so we can measure the voltage. And this electrode would be made out of silver metal. And in solution, I would have Ag+, and it would also be 1 molar. Again, this would be a standard cell. Standard meaning not like it's the one that everybody uses, but it's at standard states, okay? So I have 1 molar silver ion, I have a silver electrode, and as it being the cathode, the silver is being reduced. So basically the silver is going like this, and then the electrons are coming to meet it, okay? And in the middle we have a salt bridge, and usually that's KNO3 or something that's soluble, basically. And it's usually a high concentration. It's usually higher than 1 molar. And we don't usually state what the concentration is, but 2 to 4 molar is not uncommon. And so this completes our electrochemical cell. So this is a drawing of this electrochemical reaction. I have my anode half cell, I have my cathode half cell. The lead is actually the anode, and the silver metal is, oh, I put silver plus up here. The silver metal is actually the cathode. It's the electrode that the reduction takes place on. Now, if I'm going to write this, oh yeah, and just one other thing. I want to talk a little bit about the 0.93 volts, right? So when we say the voltage is 0.93 volts, we're saying that the anode is lower in potential than the silver electrode by 0.93 volts, or we're saying that the silver electrode is higher than the lead electrode by 0.93 volts. It means the same thing. That is, in essence, we're saying silver is above the lead electrode in terms of voltage. And that could be either that the lead is below or the silver is above. So by sort of standard, the reference that we use is based on this 0.93 volts we get for the electrochemical cell that is written. And we say that the cathode is 0.93 volts higher than the anode, which oddly makes it sound like that the anode is at 0 volts, right? Really, it's not at 0 volts. It's a relative to hydrogen, actually, minus 0.13 volts. But in reality, if you're measuring the voltage, all you get to do is check the voltage between this point here and this point here, and it tells you, yeah, 0.93 volts. You don't know necessarily where it's starting from, but you know the difference is 0.93 volts between the two. Now, when we write the cell notation, we're going to start with the anode. So the anode is lead. And then I have an interface, a change in phase coming from the lead, and it's going out across the salt bridge. So the path that we're going to take is starting at the lead, going through the potassium nitrate, and then to the silver electrode like that. Maybe a slightly better color for that. Hang on. This probably shows, yeah, this shows up better. That's the path that we're taking. So to write the cell notation, then we're going to go lead 2 plus, or lead goes to lead 2 plus. And if you wanted to say 1 molar, you would put parentheses in here and put 1 molar. And then we're going to go to the salt bridge, and so there's an interface here. So an interface is when you change phases. And then there's another interface, and that's why the salt bridge looks like 2 lines, because you're going through this interface and this interface. And then you're into the solution, so it's Ag plus, and then Ag electrode, like this. So this would be the cell notation for that particular electrochemical cell. And I did want to make one other point, that these are known as active electrodes because during the course of this reaction, they actually change in mass and are part of the reaction. They're part, like the lead is part of the redox reaction. So these are both active. Okay, so let's take a look at this one. And what you'll notice is none of these materials are actually metals. And so you can't actually make an electrode out of this. Both the ClO2 is a gas, and the ClO2 minus, right, that's aqueous. I2 is a solid, and ClO2 minus is aqueous. So let's think about how we would draw this electrochemical cell. First of all, I have to identify which one is the anode. So the anode is the iodine, because anode is the oxidation half reaction. So at my anode, I have to have something that looks like this. I'm just going to draw it for you because until you see it, it's hard to sort of get. So I'm going to have an electrode in here, and I'll talk about what it is in a little bit. And then you're going to have a solution, and in that solution, you're going to have I minus. And then the I minus is going to go on the electrode surface and form I2. So there'll actually be solid I2 forming on this electrode the way it's written. This is the anode, this is the oxidation reaction, so I minus is going to form I2. So there'll be these black I2 crystals on the surface of this electrode. Then, on the other half cell, my cathode half cell, that'll be my reduction, right? I might have to cheat and I'll just draw over this line like this. I have another electrode in my half cell. But I have more than that actually. This is like the standard hydrogen electrode. I'll have ClO2, and that's going to be a gas. So this will be at 1 atmosphere. And then I'll also have ClO minus, ClO2 minus, and that'll be at 1 molar. And what's happening here is that we're going to be going from ClO2 gas to ClO2 minus. So we're going to be going in this direction like this. And then the electrons, right, that come to this electrode, right? Again, I'll put a little voltmeter in here. Are going to come from the oxidation of the iodide, because in order to form I2, you're going to have to pull the 2 electrons out. So you have electrons coming up this way, and then the ClO2 will get reduced to ClO minus by the electrons coming around in this fashion. Okay. You'll also probably have, the way they usually do this, they'll probably have a little dome over here made out of glass, and they'll be bubbling. This ClO2 gas will get bubbled into this solution. So just like in the hydrogen electrode, we bubbled hydrogen in, ClO2 gas would have to get bubbled in at 1 atmosphere pressure, in essence displacing all the air that's in the reaction. And then we'd have a ClO2 minus in solution at 1 molar, but that's what it's converting it into. It's picking up the electron and becoming ClO2 minus. So then the question is, what are these electrodes, right? These are known as inert electrodes. And you know you have one when everything you need for the redox reaction, right, isn't a metal. If it's a metal, it's generally an active electrode, and the metal is part of the active electrode. But these are all nonmetals in here. So what kind of things do they use? Well, some of the inert electrodes that get used in electrochemical cells are typically like carbon, like graphite. Sometimes we use platinum, gold, sometimes silver, but usually not silver. Silver is a little bit too reactive. In this particular electrochemical cell, it turns out the halogens tend to be fairly reactive, and they might actually dissolve these platinum and gold electrodes. So probably not using that, probably using something like carbon. It's possible that there are other more inert to the halogen metals that could be used, but I don't know the specifics of the metal. I just know that these would have to be inert because the electrochemical reactions don't involve any solid metals for the electrode. Okay, so how do you write the cell notation then, right? So let's assume that we're using a carbon electrode. And there's reasons why we don't use carbon, but let's just pretend that it's carbon. There's reasons why we do use it, because it's really cheap and easy to find. So we're going to have carbon, and then an interface. And then we're going to have I2, and another interface, actually, because I2 is a solid, and then I minus. And then we'd have a salt bridge. And then we would have ClO2, comma, ClO2 minus. Because these, even though this is a gas, they're both in this aqueous phase. And so you would just separate them by a comma. You could, I think it would also be acceptable to put a line in here. But most likely you could just get away with putting a comma in there, and then another line, and then another carbon electrode. So electrodes on both ends could be carbon, provided they're not reacting with what's in solution. Okay, so let's do one more. Again, we have a combination now. We have the oxygen electrode. This is going to be my cathode. And then the zinc electrode, we flipped it around. So this is my anode. So this is what I'll start with. So my electrochemical cell, on the left, we'll start with zinc. And this is what I want you to do. Go ahead and try to pause it and try to draw the rest of what you see here. Okay, I didn't write the cell notation yet. Let's just make sure we got this part right. There's my kind of lame salt bridge, sorry. And the zinc is an active electrode, and in the reduction reaction, there's nothing here that could be construed as a metal, right? So this is going to have to be a passive electrode, or an inert electrode is the other word, but passive or inert electrode means the same thing. And so I didn't draw the reaction in here, but these are the things that you're going to have. You're going to have O2, you're going to have H+, and then this water, you can kind of leave it out because these are aqueous reactions, but you might also want to write it in there. So what you're going to be writing then for your cell notation. Oh, and what is the inert electrode? It could be carbon. In this case, it's probably platinum. Platinum is used for this kind of reaction a lot. Anyways, we can draw the electrochemical cell and then the cell notation from that. We're going to have zinc, right? And we're going to have zinc 2+. And again, these are going to be 1 molar, right? And then a salt bridge, and then we're going to have H+, O2, both in the aqueous phase. Even though it's O2 gas, it'll be at 1 atmosphere. And then we'll have a phase boundary, and then we'll have the electrode. So let's say platinum electrode, something like that. And then you could also put the water in there, but it's implied because it's aqueous. And so this is, again, 1 molar, 1 atmosphere, 1 molar. And if it's a standard cell, then we just leave that notation off. And then if it's not a standard cell, let's say it's 0.1 molar instead, then you would indicate the concentration by writing 0.1 molar. The cell potential for this particular cell, if you were to measure it, would be 1.99 volts. With the inert electrode being positive relative to the, so the cathode being positive relative to the anode.